Welcome back. I appreciate everybody coming back. There were some requests for some review of some of the core materials that we covered yesterday. And so we're going to take a short amount of time to review and consolidate some of the things that had been discussed relatively rapidly yesterday. And so I appreciate your patience. Some of these things may be familiar to you, some of them may be new, but we do listen to the things that people suggest, and this is a response to requests from the students. As always, I need to remind you that the lecture is live streamed and recorded, so please be aware of that. And we also have some demos that have been distributed. So I want to cover a couple of the basic key concepts. What we're going to do, though, first, I should remind you that the schedule has changed a little bit. Because we're doing this review session, everything else is going to be pushed back by one module. And so the self-guided exercise for the avascular tumor will be done tomorrow morning. I hope people will be energetic tomorrow morning, and you'll also have the evening today to review key concepts that are presented later today, so that I hope that guided exercise will be more productive. And then we'll continue as we were before. We'll have the hackathon prep session in the middle of the day as planned. So we're going to talk a little bit about some of the XML concepts that we've discussed. I want to come back to something very important that Julia talked about yesterday. And then I want to talk a little bit about some of the mechanics of CompuCell. And then we'll go back over some of the things that we did yesterday a little bit more slowly. And I hope that people are going to be able to complete all of those exercises that we tried to do yesterday. So we'll also talk a little more about tracking fields, a few extra details about plotting, which we didn't cover yesterday, and we'll see how that goes. Again, for people who are just joining, we noticed that the current release of CompuCell on NanoHub has an issue in Twedit that the Python code snippets are missing. There is a version of CompuCell on NanoHub that has the code snippets. To get there, you need to go to a slightly different module. You'll be going to nanohub.org/tool/capillary. And if you start running in Capillary and then launch Twedit there, it'll work. And we apologize that there's a bug with the main version of the tool. The tools are identical. And so this is an effective workaround. People who are using NanoHub, please log in now and go to that capillary demo and bookmark that so that you have it available for the rest of the class. Couple of key concepts. One of the things we talked about in the past few days, Julia enunciated, I think, very clearly, is the concept of the model universe, the lattice that the cells live in, and also the chemical fields. And the idea that that lattice could be two-dimensional or three-dimensional, it can be square or hexagonal lattice, and it has an intrinsic concept of a neighbor order. And that neighbor order could be nearest neighbor, the 4 nearest neighbors, the 8 second neighbors, I'm talking now in 2 dimensions, the 12 third neighbors, the 20 fourth neighbors. And the choice you make of the neighbor order, both in the Potts block and in the contact energy block, will have an effect on the way the system works. And that's a little bit unfamiliar to people because we're not used to living in a world with lattice. We're used to living in a continuous world. And so I recognize that that's something that can be a little bit confusing to begin with. The other thing that you might want to be aware of is this tag boundary X boundary, Y boundary, Z periodic. The real world, of course, is not periodic, but in computation, very often it's useful to have the edge of your simulation in one direction run into the simulation in another, essentially live in a toroidal universe, so that you don't have a change of behavior at the boundaries. Coming back to CompuCell as a whole, this single slide really enunciates all of the things that Giulio talked about in terms of the CompuCell fundamentals. The key things we're going to be talking about are cell objects. The cell objects are collections of voxels in a cell lattice. Every cell object has a unique index, cell ID, sigma, and it consists of all of the voxels which have that ID that live in the cell lattice. Those voxels don't need to be contiguous. You can have a single cell that's broken up into multiple components or fragments. And every cell by default has a type T, tau, which we use a lot. Something that we may have an issue with later on, not during this week, but going forward, is that the surface of a cell is not an object in itself. It's not a thing. It means you can't really attach properties to the surfaces of cells. If you're a center model, you don't have a volume either. In Potts, you could attach properties to volume elements, but not to surface elements. So CC3D objects automatically have a volume. I said we don't get anything for free, a few things we get for free. The number of voxels with an index that's different from the neighbors, basically counting mismatched neighbors, is the surface area. And that surface area will depend on the lattice type. You could change the interaction range for that too. The basic way we specify behaviors and interactions is through effective energies. We've talked about the volume constraint. We've talked about the surface constraint. We've talked about contact energies. Today, we're also going to be talking about chemical fields and chemical energies. And we have this modified metropolis dynamics that's stochastic, but gives us the result that we want biologically, representing cytoskeletal fluctuations, that the mean velocity of a boundary of a cell element is proportional to the force on it. The mean velocity of a cell as a whole is proportional to the force on it. Something that Giulio talked about a lot yesterday, which I think is quite important, is trying to understand what is a reasonable set of energy parameters. The effective energy change, that is a force, because it's an energy change over a copy distance, which makes it a force, compared to the fluctuation amplitude, which has the unfortunate name of T for temperature. Only a physicist would name it that. It represents, again, cytoskeletal fluctuations. It's not a true temperature. The ratio of those forces, or the ratio of those energies, determines how fast things move. And it's important to learn how to adjust parameters for reasonable behaviors. We want cells to stay relatively connected, because in the real world they do. It's all right if you have an occasional stray voxel or an occasional irregularity in boundaries. Cells do that. But you don't want a cell to burst into dust. You don't want it to shrink and disappear. You don't want generally boundaries to be totally crumpled, although there are certain cell types that do that. And so you have to think about what is a meaningful simulation. And this is an example of two simulations with different fluctuation amplitudes. The left one, there's a certain amount of fluctuation on the boundary. The right one, the cell is falling apart. And probably the left one would represent a very active cell that's migrating very actively with amoeboid motion. The right one is probably not realistic in terms of the biology. And we did this also with cell sorting. And we looked at two cases. In one case, the cells are all pretty compact and pretty round. In the right-hand case, you'll see something that's perhaps a little more interesting. The green cells are rather squared off. That means that the contact energies and the surface energies are too large compared to the fluctuations. And the blue cells have boundaries that are totally dispersed. They're mixing with each other. And that represents a situation where the boundary energies, contact energies, are and probably lambda volume are too small. And so the left-hand side is probably a reasonable set of values. The right-hand side is not so great. One of the things that we have in CompuCell, there are ways to change it, but it's a little bit inconvenient, is that the fluctuation amplitude is a property of the universe. It's not a property of the cell objects. In reality, cytoskeletal activity is a property that varies from cell to cell. In this case, it's shared. And so we have to adjust the energies of the cells to get the level of fluctuation by cell type that we want. That's something to think about. If the fluctuations are too small compared to the effective energy, then the cells won't move at all. The cell walls will line up with lattice directions. You'll see square cells a lot, or at least faceted cells with sharp corners. If the fluctuations are too big, the cells will split into multiple domains. You'll have lots of straight voxels, and the cell-cell boundaries will crumple. And so these are two sets of pathologies that you can recognize and use to fix your simulations. Even if you don't have experimental measurements, you'll know from movies how rough or smooth the boundaries are, how much separation or fragmentation of the cells you have. And so you can adjust the energies to be appropriate, even if you don't have an experimental measurement. So this is an example of using qualitative observations or semi-quantitative observations to constrain the parameters in your model. There was a question about the delta function inside the contact energy. It's simply a Kronecker delta. All right. Something that we talked about a little bit, played with a little bit, that's very useful in CompuCell is in Player, you have the ability to do steering. You can change parameter values as the simulation runs. That happens inside of the Twedit, a window, the thing that's called Model Editor. Perhaps a little bit inconveniently, you have to open up the various plugins to be able to see what energies you're adjusting or what parameters you're adjusting, but you can make those changes. Something that is a limitation of Player, and it has to do with the history of Player, is that only parameters that are defined in the XML can be edited through the model window editor. Python-defined parameters are not accessible through the model window editor. We're going to show you next week, if you come or stick around, how to do what's called the steering window, where you can open up a panel that allows you to change any parameter or variable in the system dynamically with sliders or with typed in values or pull down menus. But we're not going to have a chance to do that today. In that case, you have to decide which ones you want to change and build a window that will allow you to change those. One thing that's an issue that we're working on to fix in CompuCell is that CC3D doesn't log the changes you make in that model editor window or when you did it. And so you have to keep notes on that yourself, because if you find something wonderful and you forget what the settings were, then you'll regret it. So that logging is something that we're working on. Something that we have used repeatedly, but may be worth going over, is the initial condition specification. CompuCell doesn't have a lot of initial condition specifiers. We'd love it if somebody would like to write some more. They can be written in Python. And so if somebody has a great one that they think should be included in CompuCell, we'd love to have you do it. The two ones that we use a lot are Uniform Initializer, which specifies as a rectangular or in 3D parallelepiped volume of space from the corners, the minimum and maximum corners. Within that, there's a command called gap that allows you to space the cells They'd be surrounded by medium in that case. And then the size of the cells, and the cells are square. You don't have an option of making the cells not square. And so this is fundamentally the relationship between the XML specification and what you get. Something in general in the XML, the order in which the XML blocks are issued doesn't matter for most things. If you change the order of the plugins, it doesn't matter. However, for initial conditions, they are executed sequentially. And so if you create a block of cells with one set of rules and then another block afterwards, and they overlap, the second block will overwrite the first block. And that sounds like a problem. But if you're going to use the uniform block, the Blob initializer, which draws a circle with squares in it, it actually can be very convenient, because if I want to make concentric elements with many different elements, I want to draw a circle of cells, another circle of cells of a different type, another circle of cells of a different type. If I draw the outer circle first and then overwrite it with an inner circle, I can create concentric domains. And so if I want to make something like a tube, I can do that by using Blob initializer repeatedly. I create a blob of cells of a particular type, then I overwrite it with a blob of medium, and that'll allow me then to do tube structures. You can also do that in Python. We probably, again, need some more elaborate ways of doing this, but that's a convenience that you may want to run into later on, take advantage of. We need to go back perhaps and talk a little bit about just the basics of using Python in CompuCell. The key idea in CompuCell is that it does alternating time steps. So what CompuCell has is a concept of a MonteCarlo step. The plugins govern the MonteCarlo step. They define the energy functionals in CompuCell. CompuCell will run typically as many voxel copy attempts as there are lattice sites in the lattice. There's actually a command which we don't really use very much, called flip to dim ratio, that allows you to say, instead of going through all the lattice sites, I want to go through half of them or a quarter of them or an eighth of them. That allows you to define the step relation a little bit more delicately between the Potts steps and the Steppables. But you have a Potts step where you update the configuration of the cell lattice, and then you have a Steppable step that would run, for example, all of the things you're going to specify in Python. And you'll also at that time run the diffusion solvers and also the network analysis solvers. And so you're alternating time steps. You move the cells, you update the chemical fields, you do all the rules that you specify in Python. You update the cells, you update all the chemical fields, you update all the rules that you specify in Python. So these things are time stepped in an explicit way. And so it's important to remember that there's an alternation between updating the cell lattice and doing the Steppables. And those are done in sequence. You can call the Steppables less frequently, every 5 MonteCarlo steps, every 10 MonteCarlo steps. And very often when we're doing display, winds up plotting things is actually quite expensive computationally. So you might want to plot things every 10 MonteCarlo steps, every 50 MonteCarlo steps, instead of every MonteCarlo steps to speed up your simulations. There's also a fundamental rule in CompuCell, which is that because of the way the dynamic works, we want our dynamics to be that the velocity of a cell is proportional to the force. If you push on a cell too fast, it can't move too fast because you really only can update 1 voxel distance per MonteCarlo step. And so really there's a speed limit. There's a hard speed limit of 1 voxel per MonteCarlo step. That's the fastest something could possibly move. If you get near that speed limit, you have some strange artifacts. You keep pushing things harder, the cell won't move faster, it'll break up or die, disappear. And so you don't want to push things to move about 1/5, more than about 1/5 of a voxel per MonteCarlo step. People say, how do I relate time in real world time to MonteCarlo steps? And the fundamental answer is that you can adjust those relationships by setting parameters in the system. But there is a speed limit. If you try to push things too hard, the system breaks. And so when you're looking at a simulation, and you'll do this tomorrow, when you're applying explicit forces, if you push on a cell too much, either the cell won't move any faster or it'll break. And you always want to be in that linear region where increasing the force increases the speed linearly. And so just remember that 1/5 of a voxel per MonteCarlo step speed limit. So that means, for example, suppose that a real cell moves at a velocity of 1 micron per minute, which would be typical. Immune cells move faster, but most other cells move about that speed. If the voxel size is 1 micron, then you can't have a MonteCarlo step of 1 minute, because that would give you a speed of 1 micron per minute, 1 voxel per MonteCarlo step. That's too fast. And so you'd have to define your time step to be something like 10 seconds per MonteCarlo step or less. So that's something to think about. Let's come back to CompuCell model specification. We saw this before. We have Twedit, we have CC3D player. Inside of a model spec, there are a number of files. There are a variety that we're not going to talk about so much this week. They'll come up next week. But we almost always have a CC3DML model script, which we've worked with quite a bit. And then yesterday, we started talking about the Python Steppable script. And that's the place we're going to do our dynamic model specification. There's also a main Python script that basically strings the model together, specifies that interleaving of time steps. And we typically don't edit that by hand. That's generated automatically. Occasionally, we will have to go in and modify it, but we try to avoid that. I strongly recommend, especially now that the NanoHub people have access to a corrected editor, that people use those code snippets. The code snippets are probably the single nicest thing about the CompuCell system. It means you really don't have to remember everything. There's the CC3DML Code Snippets, the CC3D Python Code Snippets, and for people who really want to get into things heavily, there actually are C++ code snippets. If you want to actually expand core CompuCell capabilities, it's designed in the form of plugins. So actually it's written so that if you want to add an energy functional or some property of the cells in a hard-coded in C++, you can do it. And all the support you need is there under that C++ window. We're not going to talk about that this week, but I hope TJ will teach people about that next time. The biggest problem with the code snippets is remembering where things are and finding them. And so I want to walk through that. If you look at, and if you feel like following along when you're running Twedit, that would be fine. This isn't really an exercise, but you can come back and look at this again if you like. One of the things that you do have to be careful about when you're going to do the code snippets in the XML is you have to make sure that when you put your cursor in, that you're not inside another block. If you try to paste a code snippet inside of another code snippet, you'll generate errors when you start running the code. Usually the CompuCell will crash, and it may crash uninformatively, like disappearing on you. It's pretty easy to do that. So find a bunch of spaces in your code where nothing else is going on to make when you're going to paste in new information. Pull down that menu, and you have some options: metadata, plugins, pots, steppables. And these are the things that you can specify. Something that we haven't talked about much, debug output frequency, basically says how frequently things display to the console. Parallel execution is actually much more interesting. CompuCell is intrinsically multi-threaded. My current my current laptop computer is a pretty fancy one. It has 24 cores, physical cores. And that means it has 48 logical cores. And so I can actually tell it to use all 48 logical threads. And that'll speed up the simulation by about a factor of 40 when it runs. Depending on the computer you're running on, you may get how many cores you have. The speed up may be different, but most modern CPUs have at least 4 cores. And so if you ask for 8 threads, typically that'll give you a speed up of at least a factor of 4 in simulation execution. It'll also get your computer pretty hot. Even on NanoHub, you can ask for 2 cores or 4 cores, and that'll speed up your simulations. There's some other choices that you can make. And one does always have to remember that the code snippets you get are boilerplate, and some of them work out of the box. A lot of them do require you to hand edit the parameter values inside of them. Probably we should build some GUIs if somebody would like to help us with that, so that you have GUI windows to do that editing. If you try to overwrite a code snippet that's already there, you'll typically get a dialog box that says, do you want to replace the existing code snippet? Do you want to comment out the code snippet? Those are choices you have. I always recommend commenting it out so that if you want to go backwards, it's easier. One thing you may have to run into in XML is that commenting comments causes syntax errors. It's a bad design in XML. The Twedit knows about this, and it tries to do commenting of comments in a way that prevents errors. And it usually works pretty well for comment and uncomment. There's a very convenient block comment and uncomment feature in Twedit, just the way there's a very convenient indenter for the Python. If you're getting strange errors, especially system crashes, when you've edited XML, look out for commented comments. That can cause problems. If I open the plugins block in XML, in the CC3DML, I have a lot of plugin options: adhesion flex, boundary pixel tracker, cell type, and so on. It's worth actually by just going through and walking through all of the code snippets, paste them in one at a time, check them out, see what all the options are. They're really, really useful to have. Any of these we're going to talk about today. Some of them we use all the time, like contact energy. Some of them are a little bit more unusual. For example, if you have compartmental cells, there are special options for that. We'll talk about that a lot next week. We'll talk about things like external potential tomorrow. Neighbor tracker, that really should be there all the time. If you want to know whether a cell's next to other cells, you need neighbor tracker turned on. Pixel tracker, some of these things are there because doing some of the housekeeping is quite slow. And so things are set up so that if you don't need to do certain computations, you don't have to do them. Under Steppables, we've talked about Blob Initializer. You'll be learning about Diffusion Solver today. You can read in files that specify the spatial configuration of cells. Those files have that very unattractive name of PIF, Potts Initialization File. We call them PIF files. It's like a PIN number. It's a redundant name. They're not very elegant, but they work. The various diffusion solvers, we really typically only use the main one. Sometimes we'll use the reaction diffusion solver, which for some reason is not actually in the code snippets. That's a mistake. Box watcher is something that we don't use very often, don't teach, but if you have a single cell that's got a lot of space, you can tell CompuCell only to look at the region of voxels around the cell. Speeds things up quite a bit. And then we can talk a little bit more. The Potts block, again, specifies those details. Now I'd like to come back to the Steppables in Python. We promised you that we'd teach Python on the fly as you needed it. And a lot of Python is built in. Most of the boilerplate about classes and things like that, you really don't have to worry about. All you have to worry about is where your indentation starts within a given block of code. But it's important to remind you about what a Python steppable is, because that's the fundamental architecture that CompuCell uses to specify dynamics in simulations. If I look inside a Python steppable, and you can have multiple ones, they could mean one file or multiple files. Although typically for this class, we're going to just use one big steppable block for most things. You'll see some code here at the top from PySteppables import star, import CompuCell, import sys. Probably we should automatically have import numpy as NP because we use it so much. You'll often have to add that yourself. And then a class declaration, which you can ignore for the moment, but that defines the code block. And for people who are more sophisticated, any class can be used. So if you are using TensorFlow, you can import TensorFlow as a class, if you like. Then there is an init. So one thing that's actually maybe worth saying is that anything that's defined in these top couple of lines is available as a global throughout everything, all of the other parts of the system. If you define a variable, actually I should say a parameter up in lines 1 through 4 in that region, that information is available to all of the other blocks further down. It can't be written to. That's a Python peculiarity. If you try to write to a variable that you specify at the top, it won't work. It'll crash. But you can read it, so you can specify global parameters there. Inside the class, you have an init that creates the class object. You're going to have to remember that anything that goes in that init has to be after that steppable base pi _init. It's easy to make mistakes by putting things above it. There's something called frequency, which is actually the period. Frequency equals 1 means you call it once per MonteCarlo step. Frequency equals 5 would mean every 5 MonteCarlo steps, not 5 times per MonteCarlo step. So the terminology, like temperature, it's an unfortunate term. There's a start function that's called once at the beginning of the simulation. There's the step function that's called every MonteCarlo step or every n MonteCarlo steps, which is where you do the meat of things. So you use the start function to initialize. The step function is what happens all the time. And then there are exit functions. Finish is what happens if you run out of time. If you say the simulation lasts for 10,000 time steps, after 10,000 time steps, the finish function will execute. On stop is a new one. If you hit that stop button, that's executed. Because classically, that stop button doesn't do anything at the end of a simulation, and you lose information. The finish function we don't always use, but often it's useful if you're running in batch mode. You want to save a bunch of files or do analysis at the end of a simulation. That finish function is where you do that. On stop and finish are really similar. You might want to think about how to use those. As always, you have to remember indentation. You have to align your code blocks to define the architecture. And so that's the fundamental architecture. Init, not too many things go inside the init, but there are a couple tracking fields go inside the init. The start function, where you'll do your initial configuration and setup. Step function, where you do things that have to be checked all the time. That's sort of your event watcher world. Finish function, how do I output my simulations? How do I do my analysis? And on stop, what do I do if the person interrupts rather than having a normal exit? There are the Python code snippets. There are a lot of options here. There are probably too many. The ones that we use a lot would be cell attributes. I don't remember what the name for the cell pressure is, or how do I specify cell lambda volume. Those are all hiding in cell attributes. Extra fields we'll use a lot. We'll teach that today. Scientific plots we'll use a lot. Secretion uptake field integrals we'll use a lot. And visit. Gee, I don't remember how to do something to all cells. I don't remember how to do cells of a particular type. I don't remember how to do something to all the neighbors of a cell. Those are under visit. Again, I would really recommend walking through one at a time, opening each menu, pulling it down, seeing what it is, pasting it into some blank code, see what the code looks like. If you find any bugs or there's something missing, let us know so we can fix it. Please do that. Twedit allows you to have as many steppables as you want. You can divide your code into multiple steppables, and Wizard will do that automatically to some extent. It'll create, for example, a cell growth steppable, a cell mitosis steppable. You could have a plotting steppable, something that controls nutrient secretion. It's really up to you whether you put everything into one steppable or break it up into modules. Making it modular makes it easier to reuse code. Putting it all in one place perhaps makes it easier to read and debug. So it's a bit of a matter of taste. Manipulating objects in CompuCell Python. Cells and fields also are always referenced by a Python handle. We usually have the handle called cell. So we'll say cell dot something. And remember, cell is the object, dot is the attribute of the object. That's a Pythonic way of representing things. But in fact, you could call cell, you could say hello equals cell, and then it would be hello dot something. So the fact that an object's handle is the name of the object is not automatic. That's a choice. There are a lot of built-in attributes of cells. Those are referenced by cell.attribute, and that list of all of the ones and how to manipulate them is available under that Python cell attributes pull-down menu. Access modified dictionary entry. You got a sort of a hard introduction to dictionaries yesterday. They're one of the most powerful concepts in CompuCell, but if you're not a Python user, they're not so familiar. And in particular, people tend not to be used to the idea of having agents having their own dictionaries. And we'll come back to that in a minute. Attributes of the cell that you'll use all the time, cell.id. What's the index number of the cell? Cell.type. What's the type of my cell? Cell.volume and target volume. Cell.lambda volume. The pressure is available. If the volume plugin is loaded, the cell will have a pressure. So we talked about calculating the pressure by hand, but it's available to you. Cell.surface tension. There's also some information about the velocity of the cell. It's a little bit more complicated to use that Pedro will talk about tomorrow. Fundamental concept, again, that you got dumped into a little bit hard yesterday that I want to review is that CC3D keeps lists of things. And the one list that you're going to use a lot is self.cell_list. That's a list of all the cell objects in the simulation. And we're going to iterate over that list all the time. If you want to do something to all cells, you'll say for cell in self.cell_cell list, colon. And that iterator is a fundamental concept. There's also, and I'll have another slide reviewing that, an iterator by cell types. And we'll come back to that specification in a second. So if I say for cell and self.cell list, that does something to all cells. Pythonically, those four iterators are not thought of as being sequential. They're thought of as happening all at the same time. In fact, of course, they happen sequentially. But there's no guarantee in Python that the order in which you go through the cell list is preserved. In general, it is, but you're not supposed to think of it that way. In biology, there are no for loops, and there are no ifs. Things happen simultaneously. And so really, you should think about when you're designing simulations about what happens to all cells at a given time. And you shouldn't have contingency between cells within an iterator over cells, because you really should think about those things as happening simultaneously for the cells. In this case, we're printing the cell ID, the cell type, and the cell volume. It's a pretty trivial thing to do, but it's something you can do. Another thing that we might want to do, for example, would be, and we'll do this in a little bit later in this lecture, is to plot the volume and the surface area of each cell. For cell in self.cellList, self.plot when add data point, name of the series and volume here, the time, comma, the cell.volume. And so it's important to get familiar with this idea of iterating over cell lists. If cells are created or destroyed, that cell list is automatically updated. One thing you have to be aware of in Python is that you're not supposed to modify a list while it's being iterated over. And so you'll see when we create cells during mitosis or destroy cells, we'll make a list of cells that have to be divided or destroyed. And then we'll iterate over that separate list. If you change the identity of a list while you're iterating over it, that will cause potentially a crash of the system. Are there any questions about the Pythonic elements of that? Because this is a very fundamental set of concepts. One thing that's important is that the cell list is available anywhere. If you have multiple steppables, you have access to the cell list anywhere. Okay. As I mentioned, every cell has an associated type. We specify the cell type. You'll see a type ID, which is a numerical value. That's a holdout from ancient days. There's a name of the cell type. Typically, in our older code, you'll see types referenced by number. It's better practice to reference types by name. Cell.type will return the number. If we want the name, self.typename in all capital letters gives us the type ID associated with the name. So if I have a cell type cell1, and that's type ID 1, self.capital cell 1 will return the number 1. I have to be careful because most cases in Python, uppercase and lowercase are different. In the case of cell names, if I have two cell type names, which are the same except for the upper lowercase, those will be treated as the same in CompuCell. It's not that often that you'd name something cell type capital A and cell type lowercase a. But if you try to do that, it won't work. You can look up the name of a cell rather than the number with the function get_type name by cell of cell. And there are a variety of functions that I can use to go back and forth between the names of cells and their type IDs. Again, you can iterate over cell list by type. That's very convenient. I want to do something to all mesenchymal cells. I want to do something to all necrotic cells. I can iterate over multiple cell types simultaneously for cell in self.cellList by type. And then I have to list the type names. Something that I didn't mention that you have to be careful for that's different in Python and in XML. And perhaps I should have done that and made that clearer in the initialization functions, is that when you have lists in XML, you cannot have spaces in the list. So if I had cell type 1, cell type 2 in a list in the XML, I can't have a comma. It has to be cell type 1, comma, cell type 2 with no space. A space will generate an error. So that's one thing you have to be a little bit careful for in that initialization routine for blob initializer and uniform initializer. When you list your cell types, you're not allowed to have spaces between the cell types. The other thing you can do in that uniform initializer is if you want twice as many of cell 1 as cell 2, you can say cell 1, comma, cell 1, comma, cell 2. I should probably have said that when I showed that slide. I want to talk a little bit about scientific plots. You saw the introduction to that yesterday. CompuCell has a lot of different plotting functions. Fundamentally, if we want to create a plot, we have to do three things. We have to create a window on our screen in which we will display the plot. And that's done in the start function. We have to define the data series we're going to put into that window. We can have one or more. And the formatting of the plot. That's also done in the start function. And then we have to actually add the data to that data series as the simulation runs. That's done in the step function. Again, Twedit has the capability to do all of that. There's a setup, which will tell you helpfully that it has to go in the start function. And then there's add data points that goes in the step function. Erase plot is something that you use occasionally. It can be useful. And it's possible to save plots as well. That can be quite helpful for later analysis. Doesn't work very well on NanoHub. So I will, no, it doesn't use matplotlib. It uses a different library. I would have preferred it used matplotlib, but there were interaction and licensing problems with matplotlib. So again, we have to create the plot window in the data series and the plot configuration in the Python Steppable start function, and then put in the data in the plot in the step function. Again, if we're going to create a plot window, find a space, empty space in the start function in your Python, pull down the scientific plots, click setup, and it'll paste in this. And this is a case where we typically are going to have to edit what was there. The code snippets are just there to illustrate. Self.plot_plot window equals self add new plot window. So that creates a window. We have to be careful when we create a plot window. We have to give each plot window a different handle. We could say add new plot window 1. Self.plot window can be plot window 1, plot window 2, plot window 3, but they have to be different. We can't create the same handle twice. Title is required. And somewhat confusingly, you can't have two titles that are the same. I don't know why that is, actually. It has to be something about the internal representation. But the titles have to be different even if you're in different windows, you have to have different titles. X-axis title, Y-axis title are optional. Linear versus log scale are optional. Grid lines are optional. And then we have to add our data series. So if you want to add two data series to the same plot window, we can do that. And we have some basic ideas, lines, color, size of the line, dots. There are a bunch of options, and the manual lists a lot of them. One thing that you are going to have to remember is that you're going to have to match the plot window handle and the data series title exactly. And the data series variable name, mvol, here has to be matched exactly. So you have to reference back and forth between the start function and where you're doing the plotting, because you'll have to remember that. Okay. You can also apply legends, a floating legend, if you like. And there's some options about where that floats to that you can look up. Inside the step function, you're going to add the data series. Plot win has to be right. So if you called the original window plot win, it has to be plot win here. If you called it plot win 2, it has to be plot win 2 here. The data series name, mvol, msur, has to be exactly the same. Usually here we're adding data point time, comma, value. But there's no reason you have to plot x-axis as time. I could plot the volume versus the surface area for all the cells by making the x-axis the volume and the y-axis the surface area. And so you can actually create rather complex plots um, drawing lines, erasing lines, these kinds of things, if you feel like it. Something that we did already yesterday, but I want to remind you of, is that there's this concept of scope. If we define parameter values in the XML, in general, those apply to all cells of a given type or to the simulation universally. If we want to be able to vary the values in the CompuCell Python, we only specify the steppable name, and then we do the specification of parameter values in the Python. That's actually something that we probably wouldn't do today. If we were going to design the system from scratch now, what would happen is the XML would specify initial values, and then you'd be able to overwrite them in Python. And in fact, some of the newer plugins allow that. You're allowed to specify initial values and then overwrite them on a cell-by-cell basis later. But that's not universal. In particular, for volume and surface, if I want the cell volumes and surface to vary by cell, I specify just plugin name volume, plugin name surface in the XML. I must have the XML, though, to enable the use of the Python. So in this case, if I want to be able to control a volume and surface separately, I put plugin name volume, plugin name surface in the XML, and then I must specify, if otherwise I'll get 0 values, in the start function or when I create a cell, the value of target volume, lambda's volume, target surface, lambda surface. If we had different cell types, we might iterate over those. We could have random numbers modifying these values, any number of things that we might want to do. Again, if we specify things on the type level or the universal level, we can edit them in that model window editor while CompuCell is running, player runs. If we want to modify them once they're specified in Python, we're going to have to create a steering window. And there is, in fact, a nice menu inside of CompuCell for creating steering windows. Event-driven programs are a little bit more complicated, which is why we're not covering it this week. But it's not hard to do it. And there's a very good example in the CompuCell demos of how to do steering. Most of the NanoHub apps have steering panels. And so downloading and looking at that code is a good way to learn how to do that too. Very fundamental concept that you heard about yesterday on the fly is the dictionary. And dictionaries are a very Pythonic thing. They're extremely powerful. Sometimes they're so powerful that they can be a little bit intimidating. They're not universal to programming languages. They also happen to be typically a little bit slow in execution, but that's not really a concern here. Every cell object comes with a built-in dictionary. And in particular, something that is very important is that when we do cell division, dictionaries are copied automatically. Often we'll use a dictionary to add a value. Say cell.dict, square bracket, attribute name equals value. Cell.dict name equals hello. Cell.dict value is 10.6. But you can add complex objects to dictionaries. I can add a list. Cell.dict list history equals 10, 11, 13, 15. I can add a dictionary to a dictionary if I like. That's very powerful. All the operators for slicing and everything else. I can do a cell.dict list history dot append and add a value to that list. And so if I want to keep track, say, of the lineage of a cell, the history of a cell, I can add a list which keeps the history of the cell. And I can, at each time step, append the value at current time to that list. Those are rather powerful concepts. Now, of course, there are many languages that can do this. It's not unique to Python. But there are a lot of languages that don't. And so people who haven't done a lot of programming and object-oriented programming may not have run into the dictionary concept before. And so remember, every cell has a built-in dictionary, and that's where you're going to store information about cells when you're building programs. Key thing about cell dictionaries is that if you have multiple steppables, the dictionary information for a cell is available everywhere. One problem with the steppable architecture is that just as values that are defined inside of a function are not available outside of the function, they're local to the function. Values defined inside of a steppable, variables, anything else, are not available outside of the steppable. One way to do that, make them available universally, is in that header information region of CompuCell. Before you start defining your steppables, to define them there. If you read only, that works. If you want to write to them, you have to use global commands. Global commands have a bad reputation in the world of programming. They're not terrible, but they're confusing because you need to have a global that's defined both at the header and in the file you're going to use. And when you're using that subprogram, that module, you don't necessarily know if things were done right elsewhere. And so globals are sometimes make life harder when you're going to reuse code. CompuCell has a global dictionary. If our naming conventions were consistent, it should be called self.dict. And somehow, somewhere, we thought it was a better idea to give it the name shared steppable variables, shared steppable vars, which is not easy to remember. And so if you want to have information that you're going to pass between steppables, the correct way to do it is to use this dictionary, shared steppable vars. And if you do that, you can put, again, any kind of object into that dictionary. There's a trick that's, again, very Pythonic. And as I mentioned, it's something you can do even with very complex systems, like we want every cell to run TensorFlow. And that is, if you put into shared steppable vars self within, you're inside of a steppable, you assign self to shared steppable vars, all of the functions and objects in that steppable then become available for reuse. That's a bit of a trick, and people who are not Python experts should probably avoid it. But it's a very powerful function. It's also a little bit slow. One of the reasons Python is slow is it's very, very powerful. Let's see how we're doing on time. I wanted to do a couple of simple exercises on manipulation of cell properties, just to consolidate some of the things that we did. We've got about a half an hour, and so I think I will try to do a little bit of these exercises. I am not going to fire up my Twedit because I think the split screen makes it harder to read things. So I'd like everybody to fire up Twedit. If you're on NanoHub, please try that capillary workaround. And I'd like people to use Wizard, generate a 100 by 100 simulation with a single cell type, cell, turn on the surface and volume constraints. You'll always need the energy, contact energy, so remember to do that. Use Blob Initializer, and here it says to draw a sphere of cells at the center of simulation with a radius of 20, initial width of 5, and no gap. Actually, I would recommend just creating a single cell to begin with. This slide, these slides were put together a little bit in a hurry. One of the issues that we face in trying to respond to your requests is that we're up all night responding to your requests. And so I do appreciate your patience. I do appreciate your patience if there's an occasional glitch in the slide deck today, because we generated it between 7 p.m. last night and this morning. So we were trying to respond to the specific requests people made in the feedback for yesterday. So I'll give everybody 3 to 5 minutes to try to do this. And the key thing here is to create some cells. You can create multiple cells, that's fine too. And just to familiarize yourself with creating a plot window and adding to the plot window the volume of the cell. So we want to create a plot window that plots the volume of each cell. If you've got a lot of cells, you get a little cloud of points at each time. As a stretch exercise, if you're a little bit more sophisticated, you could add a little code to plot the mean cell volume or the mean cell surface versus time as a line overlaid on the cloud of points. If you want, and it's taking too much time to do a surface and volume, just do the volume. Okay. Any questions about the nature of the exercise? I also want to say that I realize our manuals aren't perfect. If you find defects in the manuals, typos, incorrect information, missing information, please screenshot the page that's offending and send us the information in the request, because we do correct the manuals when we get notices of mistakes. And if you're energetic and you want to do the manual updating yourself, you want to volunteer, we are more than happy to have you help us edit the manuals and improve them. I realize that when you're doing a lecture where you have a Zoom, especially if you only have a single screen, going back and forth between Twedit, Player, the Zoom session, a slide deck, and the manuals is not so fun. That's why we suggested printing out the basic cheat sheets to have them on your desktop at the same time. But the manuals do cover pretty much everything we're doing here in the class. Finding the information may not be so easy. Again, use Wizard. I hope people are becoming familiar with using Wizard at the moment. And then you're going to use Twedit to paste in a plot window to the start function in the CC3D Python. And in the step function, you'll paste in iterator over the cells, and then adding the data point to the plot window. There was a question about where do you put things. You will always put things in the Python Steppable function file. You almost never will use the main Python file. So you need to find the Python Steppable file. The initialization for the plot goes in the start function. The addition of points goes in the step function. Any other questions about that? Again, I'll show the result in a second. Okay, I'll give people just another 2 minutes because there are a couple of other things that we have to cover today. And people are welcome to go back over the slide deck and walk through these things again more slowly. But I do want to make sure that people get the basic idea. Somebody says that they define 2 plot windows. This is actually not if you follow the code that I have here, you won't get 2 plot windows. You'll get 2 plot series within one window. The window will open up a box on the screen. Within that box, you could plot 1 thing, 2 things, or 5 things, but they'll all be on the same axis. Okay. If somebody says that there's nothing displayed, typically if nothing is displayed, either there's a typo in the self-plot window, self-add plot new window function at the top, or when you're trying to add data series to that, you haven't named the plot window handle right, or you don't have a match between the name of the data series when you create it and the name of the data series at the end. You're allowed to generate 2 windows if you like, but that's not what's asked. There's nothing wrong with it. You have the freedom to do that as you like. Somebody says they couldn't see the window until they hit tile. So perhaps I should have reminded you that one of the most powerful things in CompuCell, but doesn't work on Macs, is that tile function in Player that will lay out your screen, that makes sure that you can see all the things that you have. Sometimes a window will be off the screen. Hit tile, it'll bring it back into the view. Okay. People can keep working on this in the background. I do want to move on a little bit. There's a shortcut for the tiling window command. I don't know whether there is. I always use the pull down menu for it under the Windows command in Player. If there is, it'll tell you what it is. It'll have an underscore on. I don't think there is. These are all great questions. There's a bit of a tension here. Yesterday, people were having trouble sometimes when there was a split screen. And so I wanted to keep up the code snippets in big enough that everybody could see them. But I realized that that means you're not seeing the player while we're doing it. Okay. So just to remind you what you need to do, you need to change your XML. Now, the next thing I want you to do, sorry about that, is to remind you how you're going to now change volumes individually. You're going to edit your plugins to just be volume or surface. You need to remember to add the slash to end the tags. And then in the start function, you'll say for cell in self.cellList and add cell target, volume, lambda, surface, and so on. So why doesn't everybody do that? Give people a minute to do that. If you don't remember the names of cell.targetVolume, cell.lambdaVolume, and so on, those are in that attributes pull-down menu inside of Twedit. All of those are there. Okay, is it clear what you need to do? In the XML, get rid of all this volume specifications and surface specifications, just bare volume plugin and surface plugin. In the start function, add for cell and self.cellList, and then these commands here. If you don't remember the iterator, go to visit in the Twedit menu, it's there. If you don't remember how you specify target volume, go to cell attributes, and it's there. There's a question, will initialization of the steppables overwrite the settings in the XML? No, that's the problem. You have to change the XML so that the XML now does not specify the initial target volume and lambda volume. That's why you have to change the plugin to be just volume slash, not volume and then the values and then volume slash. As I mentioned, for some of the newer plugins, it does work that way. And if we were going to be correct to modern practice, it should work that way. The XML should specify initial values and you should be able to overwrite them in Python. But for volume and surface, you can't do that. You have to specify it differently. Great question. I realize the first times you do this, having to go back and forth between the XML and the Python can take some getting used to. Having to remember, do you go in the start function, a step function can take some getting used to. There's a question, is the first block in the start and the second group of codes after the loop in the step? If you want to plot for all cells, the plot add points has to go inside of the loop. Again, we can come back to that. So inside of the step function, if you want to plot the value for all cells, you have to have something that says for cell and self.cell list, and then add data point, and then the value. That has to be in the iterator. If it's outside of the iterator, it'll operate once on one cell and not do it for all cells. Okay, the question about plot code inside of loops. The creation of the plot windows and the plot series, you do not want to be inside of a loop. Only the add data points are inside of a loop. There's a message about FPP plugins not being defined, turning it off. I mentioned that there's an object class called links. The computations for links are expensive. And so if they're not being used, they're not turned on. So that's why you're getting that message. It doesn't do anything. It's just a notification that it's turned off a capability of CompuCell that you're not using. CC3D works fine with NumPy. So if there's a crash with NumPy, it's almost certainly because you're making a mistake either in the way you're importing NumPy. Just import NumPy as MP. Do it that way. And it has to go in that initial line of code at the very beginning. Don't import it inside of a steppable. And it's almost certainly that you've got a typo using the NumPy call. There's a question about using blob instead of rectangle in Wizard. There should be a tag called radius in the XML. That should be generated automatically by Wizard. In fact, I know it's generated automatically by Wizard. You specify the position of the center of the circle and then the radius of the circle. If you go back to the slide, I shared the slide deck again. If you go back to the slide that I gave you, you can look that up. We're not going to run these exercises now, but there are a few things I do want to talk about. The next step in this exercise, if you're going to do it all out, would be to plot the pressure and the surface tension. The pressure and the surface tension are actually available as cell attributes. The pressure, the internal pressure, cell dot pressure, is backwards from what you expect. If the cell is under compression, you'll get a positive value. Or sorry, negative value. If the cell's under tension, you'll get a positive value. That's a little bit surprising. If people are feeling comfortable with this, you could add plot windows for pressure and surface tension for each cell. Something that you'll want to do probably fairly often is do something every so many MonteCarlo steps, not every MonteCarlo step. You can control the frequency with which a steppable is called by changing that frequency command. It should be the period, but the command. But within a steppable, there are a variety of ways to do that. If you do if not MCS% and then an integer, that will do something every that many steps. If not MCS%10 : will call the thing every 10 MonteCarlo steps. For things like plots that take quite a bit of time, very often you'll want to delay things. If not MCS%100, if not MCS%5 is a useful thing to remember, little trick. I do want to come back to something, and this is the one other exercise I really would like people to do, which is tracking fields. Tracking fields are probably the single most powerful analysis and display functionality inside of CompuCell, and it's a unique feature. I don't know any other packages that are competing with it that have it. A tracking field allows you to display inside of the boundaries of a cell the value of a variable. And it's done automatically, and it's done in a very powerful way. This is one of the rare times when something goes not in the start function, but in that init function above the start function in the steppable architecture. And again, in the in the Python menus, extra fields automatic tracking, and there's an option, track scalar cell attribute, track vector cell attribute, which is fascinating, and I recommend you investigate, but we won't talk about this week. And there's also the ability to do some customization, which is an advanced feature. The one we use all the time is track scalar cell attribute. And so you go in use that pull down menu, and it will paste in, and it's critical that this go after steppable base pi __ init. If you put it before that, it will crash. If you put it inside the start function, it will crash. It has to go after the init. And it will paste in something called self.track cell level scalar attribute. Field name, you have to give that name something. It's just a placeholder. You could call it pressure, temperature, volume, anything that you feel is useful. They have to be unique. You can't create two fields with the same name. And then attribute name. And that's the name of a variable. It's the name of a dictionary key, to be specific. Then within the start function or step function, if you create cell.dictionary attribute name, whatever you called it in the steppable base pi, and then assign it a value, it will automatically display it. And so I would like people to try this out. Add a tracking field for the pressure in your cells. And that's the last exercise we're going to do. I'll walk you through some of the principles of mitosis after we complete this exercise. But I want you to go into the init. Remember, it has to go after the init line and add, using Twedit, the tracking field. You're going to name the field pressure. The attribute name will be pressure. And then in the loop that you've just generated to add the data points, add a loop that says cell.dict pressure equals cell.pressure. Now in player, to display this, you're going to have to add a display window. And so I believe you've seen how to do that. Maybe we should do that together. Perhaps people can figure that out on their own. There's a switch which will allow you to display different options, cell fields, chemical fields, and so on within player. So perhaps we should look at that together. I'm going to switch over to the other window just for a second to show you something with player while you're doing that. Okay, here's player running. I have a cell that's not doing anything. It's not a very interesting simulation. I'm going to run it. And here I'm going to start out with cell field. So here's my cell. And it's sitting there not doing very much. And now I'm going to hit pause. I can create a new display window by hitting new graphics window here. So that's a useful function to have. And then I'm going to hit tile to lay it out again. And for some reason, it doesn't draw it correctly to begin with, but it should redraw in a second here if I nudge it. And now I see cell field twice. I don't want cell field twice. I come here, I pull down, and that's probably not visible to you. It pulled up the window in a sort of a funny place. If I pull down here under cell field, there we go. I can select internal pressure, which is a tracking field. And now I can run and display the tracking field. So does everybody get that? It'll take, again, maybe a few minutes to get used to that. But I want people to see how to do that. Again, it takes time to practice and play with all these options. There's a question about the difference between the field name and the attribute name. Both of these are the names of handles or variables. And so you have the freedom to make these what you like. They don't have to be the same. They're allowed to be the same. One of them will show up when I pull down that menu, you'll see the name of the field. That's going to show up in player as the name of the field. The value cell.dict pressure is simply got to be the same between attribute name when I create the tracking field and the dictionary entry. It's telling you what dictionary key to use to plot. I tend to use the same name repeatedly, pressure, 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 so that I remember what I've done to be consistent. But if I wanted to call one cell pressure, the other one internal pressure, and then I could do that as well. The tracking field must be in the init, and it must come after the init command. If you put the tracking field command before the init, you'll get an error. Let me come back. I showed that here. You have to have that sequence. So again, in the step function, you do cell.dict attribute name equals value. In this case, cell.pressure. Attribute name would be replaced with pressure. Field name would be replaced with pressure. Somebody says that when they create a new graphics window, they don't have the option of displaying the tracking field. That's possible. That could be a bug in the new release of CompuCell. So see if that persists. If it does, please screenshot it and describe it, and we'll try to fix it. There's a question about creating new windows from inside of CompuCell. So certain kinds of windows can be created. For example, plot windows can be created. Field windows in general have to be created by player. They can't be created inside of the Python. We don't have a command for that. Yes, I know the drop-down menus sometimes show up in strange places. I'm not sure what the issue is. That seems to be a PyQt issue. No, the names of the fields or the variables don't have to be capitalized. They can, but they have, whatever capitalization you use has to be consistent, but they don't have to be capital. They can be lowercase. One thing that you can do, and this is desktop only, is that you can save plots. You can save plots from within Python, and there are commands for doing that in the Twedit menus. But you can also do it from player. This will not work in the NanoHub. If you hover over a plot window and you hit right click, it's going to give you a variety of options. Some of these options don't work, I have to say, but export does work. And so if you hover over a plot and you click export, it will give you the option to export it as an image or as a CSV. And when you do that, then you have those data available for you. And so that's something that can be quite useful to save the images. Instead of having to screenshot them, you can save the image and you can save the data series, which is also quite useful. Sometimes you don't want to go through the trouble of writing all of the file handling in the code until you know you need it. And so being able to save it on the fly is quite helpful. I also want to just discuss, I just want to talk for a minute about cell growth, because I really do have to let us get on to the next deck pretty soon. Gilberto covered cell growth very nicely yesterday, but it went by pretty fast. Again, if we're going to have cells grow, we can only specify volume in Python. So we need the volume plugin loaded, nothing else. In the start function, we'll define the initial values of cell volume and lambda volume. And then in the step function, we'll have something that increments the cell volume. And we'll use that plus equals for cell.targetVolume equals cell.targetVolume plus a number. Ideally, we'd go through a little exercise. The code that you have now can be turned into a growth code by adding one line, which would be to add to your, when you're iterating over your cell list, say cell.targetVolume plus equals some number. That will do that for you. If you do that with the surface energy turned on, the cells will get compressed. So you have to make the surface increase in parallel with the volume. Just to make you, to review what the code would look like, in the start function, you would specify the initial size of your cells and their lambda volume. In the step function, you'd increment the volumes each time. If you do that, you'll get a single growing cell. If you want the cells to divide, you have to use a special steppable. This is one of the few times you actually have to separate steppable, called Mitosis Steppable. And there are a lot of things that you have to decide, in particular, how cells triggers division and what happens when division happens. Is division on the oriented plane always the same direction, in a random direction, major axis or minor axis of the cell? You're also creating a new cell. When the new cell is created, the daughter cell is created, you have to decide, one, how the volume is allocated between the parent and the daughter, and two, what the attributes of the daughter cell are. You don't get anything for free, so if you don't say the daughter cell has attributes, it doesn't. Typically, the target volume and surface are things you have to adjust. If it's a symmetrical division, then typically you'll reduce the parent volume by 2 and then clone. And so again, the basic structure of Mitosis Steppable is the following. You have a class Mitosis Steppable. In the Mitosis Steppable, because we can't change our cell list while we're iterating over it, we create a blank list, cells to divide. Square bracket is a blank list. We go through our cell list. We have some criterion, some trigger for cell division. In this case, it's just, is the cell bigger than 50 units? If it is, we use the append function. That's how you add things to a list. Cells to divide dot append cell. And so now when we've run through that, we have a list of all the cells that are bigger than 50. We can't do it one at a time because it would break the cell list. We then run through that list of cells to divide, and we divide them, in this case along random orientations. And this is all boilerplate code, which you'll get from Wizard. Once we've divided a cell, we have to say what happens to the daughter cell. In particular, we're going to say that the parent loses half of its volume, and the daughter cell has all the properties of the parent, including half of the volume. That's the simplest possible thing. You can control what's copied, what isn't copied. You can change individual things like cell types, for example, but that's the basic structure. You decide what cells to divide, you put them in a list, you iterate over that list, you do the division, and in update attributes, you decide how the volume of the child relates to the volume of the parent, and how the properties of the child relate to the properties of the parent. And that's really critical. If you want to add mitosis to a program you've already written, where you didn't have it before, there's a function in Twedit. If you click on CC3D Python, right-click, add steppable, that will give you an option to add additional steppables. If you add a steppable called mitosis, click mitosis under steppable type. You can also create those tracking fields here if you want. It'll do that automatically for you. Hit OK, and that will automatically generate that. You can also add the mitosis steppable in the CC3D Python menu under Add Steppable, and it'll give you the same dialog. So there are two different ways you can invoke the Add Steppable function. And it'll also automatically update the registry of steppables in that main Python file that you don't want to be editing by hand. Again, if you have multiple steppables, variables inside one steppable are not accessible in other steppables. If you're going to share them, use steppable shared variables to make those things available across steppables. Okay. So again, here's Mitosis Steppable. We go cells to divide, empty list, iterate over cells, condition if cell volume greater than 50. We append that cell to the list of cells to divide. And that's a typical structure we'll use, but the conditions may be more complicated. We may only iterate over certain cell types, but we'll see this over and over again. Once we have the list of cells to divide, we have to iterate over that list for cell in cells to divide. So iterating over lists of cells is something we do all the time in Python, CompuCell. And then we have to do the division. And we'll see here we're dividing by random orientation. You could have a fixed orientation, division along major axis or minor axis. We then have to update the attributes. Typically, the first thing we'll do is say the parent has half of the volume it had before. Often we'll say it has half the surface it had before. And then we'll clone the parent attributes to the child. By default, we're going to do that. We're always going to clone, and then we'll overwrite values that we want to change, because there are too many attributes that we might want to have to copy at the same time to want to do them one at a time. Sorry. Okay. And so if I had a little bit more time, the exercise would be adding cell growth, which is one line of code, really only one line of code, and then adding the cell division, which is adding that one's Mitosis Steppable. And again, that Mitosis Steppable is all boilerplated in. So if I do this process here, maybe people should take a minute to try that. You add that Mitosis Steppable. The one thing you'll have to do is get rid of the cell type change at the end. And so I hope that gives you a little bit of a review of the things that we did before. If you do it, you should get a result like this. It's where Gilberto was showing you yesterday afternoon. You'll see that cell pressures will blow up because you keep creating cells in a finite volume. I hope the review was helpful for people. There's a question about how the cloning is done. It is a deep copy. It uses Python deep copy. That's right. So the other thing that I wanted to do, which I won't talk about today, I'll just, again, flash a slide just to let you know it exists, is that besides scientific plots, time series or point plots, you can plot histograms. And it's quite convenient to be able to plot histograms. There's a function in the Twedit menus that tells you how to plot histograms. They look a lot like the scatter plots that we've been doing. The difference is that you have to have a list of the things that are going to be histogrammed. And so you'd create a list, for example, of the pressures. You append all the values of the pressure to the list, and then you ask the histogram to create a histogram from that list. And you have to decide how many bins to use, how often to update it. There are a variety of functions, but you can create live histograms, and that can be a very useful way of communicating ideas. And so I definitely would recommend people trying that out on your own when you have a few minutes. So I hope that people are able to get through at least parts of this. I realize that there's a lot in this lecture. I realized we went over it really too fast yesterday. And so I hope that going back over it today is helpful. And you'll have the slide deck and the videos to go back over this again if you'd like to do that. There was a question again about how the copying is done, the cloning is done. Yes, it does use Python deep copy, as I said. There's a comment about the plot windows freezing. When you create a new plot window or you change the plots, you always, that pauses the simulation. So you always have to hit play again after you change the configuration of the plot windows. See if that's what's going on. If it's actually crashing CompuCell player, that's a different matter. But try hitting play again and seeing if that resolves.